It's my honor to be here, and this is my second time to come to Middle East. My first time was in 2016 in Qatar for the World Cup. So still feel very excited for the weather and the food here. Today I will share our work about overcoming heterogeneity challenges in federated learning. Different from the style that Yaodong and a few presenters did earlier, I will not focus on one single work. Instead, I will give a gallery of some related work. And thanks for the earlier speakers have set up the good foundations of introducing the notations, and I will directly go to the methods. Oops. So we know that AI has shown its power in many tasks. For example, the ImageNet classification challenges and the segmentation tasks. So those amazing results are typically achieved using the natural image data. However, when we look at the real-world data set, for example, medical imaging, that's what I trained from. I work on neural imaging during my PhD, but still I'm working on different types of medical images. We found that the real-world decentralized data actually are not ideal. They suffer from the heterogeneity issues, such as feature shift. We have the MRI scans for brains from different centers. As you can see, the pixel densities are different. And we may also have the label shift issues, namely the class prior distributions can be different for different centers. And we also have different sensors that cause different data collected. When we look at the heterogeneous data, some issue may occur. So these are two figures from the original Fed average paper. The conclusion is here. Convergence to the optimal model can be typically guaranteed to the IID data. However, issues arise in strongly non-IID data. And in order to do the optimization of federated learning on heterogeneity, a traditional way is to optimizing a global model, such as this is a figure from Scaffold, which analyzed the training trajectory from two heterogeneous clients. And this paper suggested that we will have the client drift issue, particularly when you use a very large local update epoch. So in order to ensure the convergence when you're optimizing a global model, people typically require small local updating epoch or adding some regularization. Both strategies can slow down the convergence. There are another strategy called personalized federated learning. We have heard about this terminology many times. So this allows different clients to learn a little bit different models. For example, part of the model parameters may be shared and some are different. In this case, we need to design some objectives for them separately, but still enforce them to collaborate. Next, I will introduce our field work, how we leverage personalized models in our setup. So skip a few slides. Okay, so the first work I want to introduce is FedBN, federated learning on non-ID feature via local batch normalization. Maybe some of you have heard about it, and this paper was published several years ago. Here we focus on the issue of feature shift. Mathematically, we define the definition as follows. So our proposal is as follows. Compare with the original Fed average where you share all the model parameters. Here, we suggest all the clients keep their batch normalization parameters locally involved rather than averaging on the server. This is very easy to implement. You only need to change the aggregation strategy. We have the toy example to show that if you're only averaging the non-BN parameters, you will have a much lower generalization error in this toy example. We also did the experiment on the benchmark data set, and as you can see, compared with some other methods, we can perform the best. This is the old comparison, and I know people now use FedBN for new data sets. Some of you may notice that FedBN cannot achieve good performance, but later when we examine the data set setting, they use FedBN for the label shift setting. Here is more like a clarification. We show FedBN originally, particularly for the feature shift issues. Another interesting phenomenon we observe is that FedBN actually can converge faster than at Fed average. So this figure shows the learning curve for FedBN in the solid line and the Fed average in the dashed line. We have the zoom-in version here. As you can see, the solid line is underneath the dashed line. So we also conducted a theoretical analysis, which is based on our Fed NTK work. We calculated the kernel matrix for Fed average and Fed BN. We found that the smallest eigenvalue of the kernel matrix of Fed BN is equal or greater than Fed average, the equal sign achieved when you use the IID data. So in this case, we theoretically justify why Fed BN can converge faster than Fed average. So as you can see, a simple strategy by personalizing the generalization layer can boost the performance of federated learning on heterogeneity data. In addition to the feature shift issue, we also look at the label shift issue. There are many work addressing the label shift issue, but here we are dealing with a more challenging setting. Here are the practical scenarios that we're looking at. The class priors or label distributions are different due to the demographics. And also, we consider that if we set up the federated learning across hospitals, the hospitals may hold unlabeled datasets, in short, USET, due to the absence of the budget or the expertise. And nowadays, when we talk about privacy, we can also claim that hospitals don't want to share instance-wise labels. Here is an example that maybe one hospital only want to report that 85% of the population, they are healthy control, and 50% of them are patient. For another hospital, they may claim that we have 90% of the healthy control and 10% of the patient, and so on. So given such a setup, can we train a classification model to classify each instance as a patient or healthy control? To this end, we leveraged the unlabeled learning strategy, which was developed in centralized learning and adapted into this label shift issue. So firstly, for each hospital, we randomly cluster these data samples into M sets. So these M sets formulate this surrogate task. We use the index of the unlabeled sets, in short, U sets, as the surrogate label, and then perform the traditional Fed averaging to do this surrogate supervised federated learning task. Now the question is that, given this surrogate federated task, how can we infer our desired classifier from the surrogate federated learning task? In our paper, we bridge the class priors between this surrogate task and our desired task as follows. Suppose the true class probability is defined as eta C, and the surrogate class priority is defined as this dash eta C. So we show that these two probabilities can be connected by a transition matrix QC. And see our theory 1 for details. Then what this QC will be used for in our case? Let's go back to the traditional federated learning setting. For the surrogate task, we have to train a neural network. And then we just add this QC, suppose we know what QC it is, onto the output of the neural network. So this QC can serve as the personalized layer to fit the shared models into the heterogeneous label distributions. And what is this QC? We show that QC actually can be calculated from the class priors. But in practice, the class priors cannot be known in advance. In this work, we assume that we know it. So following this work, we consider a practical setting that we have some information for us to estimate pi c. In this case, we assume that the server may have a small amount of data, labeled data. However, all the clients, they have the unlabeled data. And also, their label distribution, the underlying label distribution, is heterogeneous and imbalanced. To retrieve this, the first step will be estimating the class prior. We follow in the traditional pseudo-labeling strategy. First, we build a dynamic bank and then try to calculate the pseudo-labels. We don't count in all the samples. Instead, we consider the confident samples. But that's not sufficient. If you consider the imbalanced data, different class may have different confidence score distributions. So in this case, we actually use two different thresholds to encourage the minority classes also can include some samples in the dynamic bank. So we can estimate the class priors better. Once we obtain the class prior, we formulated such a semi-supervised learning problem as follows, which is a combination of the supervised learning loss on the server data and the unsupervised learning loss on the client data. Given only a few minutes left, I want to introduce our another recent work where we discussed the device heterogeneity. Different devices have different computational powers, so we have to customize the model structures to fit in their capacity. So in this case, we follow a strategy called pruning, or in another word, we mask out some parameters so that for some device with smaller capacity, we train less number of parameters. Then the question comes to how should we design the masking vectors? Here we divide the model into two parts. One part is the body model, which is the big chunk of it, and another part is the head model, only a few multi-layer perceptions. So on the client side, we say that let's apply this masking vector onto the gradient of your updating that fit your capacity. And on the server side, when you do the aggregation, so you calculate this normalized masking vector and then put onto the aggregation step. In addition, we say that the server needs to determine the best masking vectors following this additional optimization objective. Why we have this term? This because we conducted the theoretical analysis and found that we have this additional bias term in our convergence bound. So we want to minimize this additional bias term. In addition, after training, the personalized model will be fine-tuned based on their local data. And more recently, we claim that personalized model may not be the best solution. We found that there will be a trade-off between the personalization and the generalization. And here's why. So in personalized federated learning, we focus on the local performance, so you get the lowest loss based on your local testing data. However, when we check the global loss at this local optimal parameter, it may have very high global loss. So our proposal is that, can we have a sweet spot, which is in this yellow star? Well, we may not get the optimal for your local loss landscape, but at this point, we have a relatively low local loss and also a relatively low global loss. In this case, we have a good trade-off between your personalization and generalization. So how can we achieve this? We modified the widely used local fine-tuning strategy in personalized federated learning, motivated by the model soup work. Model soup is a model ensembling strategy that improves the generalizability of your neural network. So for each client, we use their validation data to select some global model. Noting that in the traditional personalized federated learning, you only focus on this last round of global model and then do fine-tuning. But in this work, we say that let's collect more ingredients to make a better soup. So for each local model, we look at all the global model trajectory and then select the good ones. So when we do the local fine-tuning, in addition to the fine-tuned model, we also perform further interpolation with the selected good global model. So in this version, we found that we can improve the generalizability while didn't decrease the personalization performance that much. Some ongoing work, we try to make the soup better and more delicious. So my student proposed that let's make more richer ingredients in the local model by performing some random masking. So in this case, when you do the local fine-tuning, you can generate multiple local models by random masking strategies. As the preliminary results show here, when we performed 80% of sparsity pruning, we can achieve much better performance than using unpruned local model. This is pretty much of my recent work on tackling the data heterogeneity issue. I want to say acknowledgement to my collaborators. and my fantastic team at UBC, and my funding agency to support all this work. Thank you for listening, and here's a quick overview about our work, and then touch from these different regions.
Any questions? Maybe I can ask one question about the, you mentioned that I guess you mentioned the global performance as like a proxy for generalization. Can you talk a bit more about why that's a good, like doing well on the global laws was the connection to that with generalization?
Yeah, so the question is about why we link the global laws to the generalization. I have to say that's not the exact link. For here, we assume that actually if we consider some kind of like testing data, like what Xiaotong earlier mentioned, it may be a linear combination of the local distribution. So in this case, when you look at the global loss, you can approximate the generalization performance. Yeah, that's a great question.
Oh yeah, there's a question at the back.
Hi, thanks for the talk. My question relates to concerning the intersection of masked models when you're doing the FedSoup. Do you have any insights on what coverage you should have over an aggregation round? Like how much coverage you need to have across different, let's say, paths or sub-models that you're aggregating?
Yeah, so if I heard correctly, you are asking how many models did we use for the ensembling or interpolation? What's the question?
Yes, or the intersection of these models, how much of the actual model it needs to cover in order to work and converge?
Yeah, so in our case, we use around 3 to 5 models in the first version, but in the second version, so we do the hierarchical interpolation. So when we have the diverse local model, we do the first level of interpolation. In this case, we typically use 5 to 10 local model, and then in the next step, when we integrate with global model, we didn't increase the total ensembling models. Yeah.
Thanks.
But actually, that's a more heuristic hyperparameters. Maybe for different data sets, you need to choose a.
And this is cross-silo, is that correct?
Sorry?
This is cross-silo setting.
Yes, for our experiment, we assume the cross-silo settings.
Yeah. Okay, great, thanks.
Yeah, thanks.
We next have